Some objects pass through space and are forgotten. Others pass through quietly and leave behind questions that refuse to fade. 3I Atlas belongs to the second category. When astronomers first detected the object later designated as 3I Atlas, there was no immediate alarm. Interstellar visitors are rare, but they are not unprecedented. Objects can be ejected from distant star systems during planetary formation, stellar encounters, or gravitational disruptions, then wander the galaxy for millions, sometimes billions of years before briefly crossing paths with another star. Most of these visitors behave predictably. They drift, they tumble, they react passively to radiation, gravity, and heat. 3I Atlas did not. The first sign that something was different appeared not in its brightness, but in its motion. Orbital calculations revealed that Atlas was traveling on a hyperbolic trajectory, meaning it was not gravitationally bound to the Sun. This was not an object captured into an orbit. It was passing through once at extreme speed and would never return. Its velocity exceeded solar escape velocity by a wide margin. In practical terms, the Sun could not slow it down, capture it, or significantly alter its course. Atlas was a visitor with no intention of staying. That speed alone confirmed its interstellar origin. But speed was only the beginning. As Atlas moved deeper into the inner solar system, it became the focus of coordinated observation. Multiple instruments began tracking it simultaneously, not to confirm a discovery, but to rule out error. Data arrived from independent platforms operating under different conditions. The James Webb Space Telescope recorded infrared signatures. Hubble provided visible light imaging. Ground-based observatories contributed spectroscopic measurements. The observations aligned. What they revealed was unexpected. Sensors detected motion originating from within the object itself. This was not surface shedding. It was not debris being pushed outward by solar heating. The displacement appeared internal, subtle, directional, and persisted, as though mass inside Atlas was shifting rather than escaping. In physics, this distinction matters. Surface activity reacts outward. It dissipates energy. Internal movement suggests resistance, something responding to stress rather than simply absorbing it. Initially, researchers treated the signal as noise. Deep space observations often contain false positives. Instruments were recalibrated. Background interference was removed. Timestamps were cross-checked across platforms. The anomaly remained. Shortly after internal motion was confirmed, a second anomaly followed. Thermal sensors registered a sudden temperature drop inside the core of Atlas, approaching 100 degrees Celsius. The change was rapid, nearly instantaneous. It was not gradual cooling caused by rotation or shadowing. Atlas had not entered a region of reduced solar exposure. There was no environmental explanation. For an object bathed in sunlight, such a rapid internal temperature decrease implied active heat absorption, not passive cooling. Then came the pulses. Electromagnetic detectors recorded a sharp emission from Atlas, then another, and another. Each pulse occurred at precise, evenly spaced intervals. The timing was exact. The rhythm did not drift. It did not decay. It repeated. In nature, regularity of this kind is rare. Gas outgassing produces chaotic bursts. Fracturing ice releases energy unpredictably. Even crystalline stress responses vary in timing and intensity. The emissions from Atlas did not. They followed a pattern. NASA's public description of the event was deliberately cautious. The phenomenon was labeled an unclassified thermodynamic fluctuation. The language was accurate, but intentionally non-committal. Inside scientific discussions, however, the word used more often was anomaly. In science, an anomaly is not a conclusion. It is a warning. As Atlas continued its passage, visual observations added another layer of complexity. High-resolution imaging showed that the shape of the coma, The cloud of gas and dust surrounding the object was changing faster than expected. Within days, Atlas appeared stretched and asymmetric. The once rounded inner region elongated along a single axis. The tail split into two diverging streams, forming a shallow V-shape rather than a unified plume. Such bifurcation typically requires a gradual shift in jet orientation. No such rotation was observed. At the same time, polarization data revealed uneven dust behavior. One side of Atlas scattered light in a way consistent with larger, denser particles. The opposite side showed finer, more porous material. This imbalance suggested directional ejection, not uniform surface activity. Despite this apparent chaos, one variable remained stable. The net thrust direction of Atlas did not significantly change. If new jets were activating randomly, the thrust vector would have shifted. Instead, the data indicated that activity was intensifying in existing regions, not migrating across the object. This pointed toward deepening fractures or widening internal vents rather than the formation of new surface features. Chemical analysis complicated the picture further. Spectroscopy revealed that Atlas was releasing carbon dioxide as its dominant volatile rather than water vapor. This alone set it apart from most known comets. Carbon dioxide sublimates at higher temperatures than water, suggesting formation in an environment colder or chemically different than those typical of our solar system. More puzzling still was the detection of nickel vapor alongside unusually low iron signatures. In known cometary material, nickel and iron tend to appear together. The ratio observed in Atlas did not match known solar system compositions. None of these observations violated the laws of physics, but taken together, they strained existing models. As scientists worked through familiar explanations, outgassing, thermal cracking, ice sublimation, crystalline stress, each accounted for part of the behavior, but none explained all of it simultaneously. Internal motion, rapid heat absorption, rhythmic electromagnetic pulses, magnetic field fluctuations, asymmetric structure, and unusual chemistry formed a sequence, not a collection of isolated events. The order mattered. Internal movement came first. Thermal absorption followed. Electromagnetic emission came last. Coordination is difficult to attribute to coincidence. Still, no extraordinary claim was made. No conclusion was drawn that Atlas was artificial or intentional. Instead, researchers confronted a more uncomfortable reality. Current models were insufficient. Atlas did not behave impossibly. It behaved unexpectedly. And that distinction marked a turning point. From this moment forward, 3I was no longer treated as a passive interstellar remnant. It was treated as a system, one that could change, respond, and briefly activate under the right conditions. What triggered that activation, and what it revealed about the interior of Atlas, would become the central question of the investigation. That question remains unanswered. By the time 3I Atlas reached the inner regions of the solar system, the tone of the discussion had changed. Early curiosity gave way to restraint. The data no longer inspired excitement, it demanded caution. Atlas was no longer being asked what it is, it was being examined for what it is not. This shift marked the most critical phase of the investigation. In science, elimination is often more powerful than discovery. The first explanation to be tested was the most familiar one: cometary outgassing. When volatile compounds inside a comet warm, they sublimate, escape through surface vents, and generate thrust. This mechanism explains jets, rotation changes, and tail formation in countless known objects. But Atlas resisted this explanation. Outgassing originates near the surface. The internal movement detected in Atlas did not. It appeared deep within the structure. More importantly, gas-driven activity is chaotic. It varies with temperature, pressure, and structural weakness. The emissions observed from Atlas followed a precise rhythm. Nature rarely keeps perfect time without feedback. Next came thermal cracking. As objects heat unevenly, stress fractures can form, releasing energy and material. This process explains sudden brightness changes in some comets. Yet thermal cracking releases energy outward. It does not produce rapid internal heat absorption. It does not generate electromagnetic pulses at fixed intervals. And it does not synchronize with magnetic field fluctuations. Thermal stress alone could not account for the sequence observed in Atlas. Ice sublimation was also considered. Different ices respond at different temperatures, and layered composition could explain uneven activity. But sublimation lacks precision. It erupts, it fades, it does not pause, reset, and pulse with identical timing. Crystalline flexing, another exotic but natural explanation, also fell short. Some crystal structures can store stress and release it under radiation. However, crystalline behavior does not generate sharp electromagnetic spikes, nor does it coordinate motion, thermal change, and magnetic response in a clean sequence. Each explanation failed not because it was impossible, but because it was incomplete. This is where the uncertainty sharpened. If Atlas was not simply reacting to its environment, researchers had to consider whether its internal structure was fundamentally different from what existing models assumed. Not artificial, just unfamiliar. This line of reasoning gave rise to what became known as the shell hypothesis. The shell hypothesis does not suggest that Atlas is a machine. It proposes that Atlas may consist of a dense outer layer encasing a more complex, heterogeneous interior. Such a structure could form naturally under extreme interstellar conditions. Over millions of years, radiation exposure, micrometeorite impacts, and thermal cycling could harden the exterior while preserving volatile-rich material beneath. A shell would explain several observations at once. It would isolate internal processes from surface behavior. It would allow heat to be absorbed internally without immediate surface response. It would also permit long dormancy, followed by brief activation when specific environmental thresholds were crossed. That threshold may have arrived near Jupiter. Jupiter possesses the strongest magnetic field of any planet in the solar system. Its magnetosphere stretches millions of kilometers into space, interacting with charged particles far beyond the planet itself. As Atlas passed through this region, subtle but measurable changes occurred. Color shifts appeared briefly in the coma. Emission intensity fluctuated in ways not consistent with solar heating alone. Most notably, internal activity within Atlas coincided with localized magnetic field strengthening around the object. This correlation was difficult to ignore. If Atlas contains conductive or magnetically sensitive material, Jupiter's magnetosphere could induce internal currents. Such induction would not power the object. It would act as a trigger, similar to how certain systems activate only when precise conditions are met. This interpretation remains speculative. Natural bodies can respond to magnetic stress without design. Interstellar objects may contain materials rarely seen in our solar system. But the timing raised a critical question. Why did Atlas remain dormant for millions of years, only to briefly activate here? As Atlas continued its passage, another anomaly emerged. The object began to change shape rapidly. Images taken days apart showed stark differences. The once symmetrical appearance gave way to elongation and internal asymmetry. This was not a trick of perspective. Multiple instruments confirmed the transformation. Such rapid evolution is unusual. Comets typically change gradually as heating increases. Atlas altered on the scale of days. The tail split, the coma stretched. Yet the overall thrust direction remained stable, suggesting that the same internal regions were becoming more active rather than new ones appearing. This pointed toward deepening fractures, not surface chaos. Spectral analysis supported this view. The materials being released appeared stratified. Larger particles dominated some regions, finer dust dominated others. Infrared data revealed an unexpected thermal inversion, with outer layers retaining more heat than the core. These observations suggested exposure of ancient internal layers, material that had not interacted with starlight since Atlas formed around another star. In this framework, Atlas was not transforming into something new. It was revealing something old. This reframing mattered. The object was no longer viewed as a singular body, but as a record, a layered archive of interstellar history. Each burst of activity acted like excavation, exposing deeper strata shaped under alien conditions yet governed by familiar physics. Despite the dramatic behavior, one fact remained consistent. Atlas did not violate any physical laws. It expanded the range of known behavior without breaking the rules. That distinction guided scientific restraint. Speculation inevitably followed public interest. Delayed imagery and observational gaps fueled rumors of concealment. Claims of deliberate secrecy spread online. None were supported by evidence. When official data resumed, the images showed nothing extraordinary, only a highly unusual natural object moving away from the sun. By then, the most active phase had passed. Atlas exited the inner solar system, carrying its secrets with it. No final confirmation was possible. No decisive experiment could be performed. The record remained incomplete. And that incompleteness is the true conclusion. 3. Atlas did not provide proof of design or intention. It provided something more difficult, a reminder of the limits of current knowledge. The object occupied a narrow space between explanation and mystery, where uncertainty is not failure, but frontier. In the end, Atlas leaves behind no answers, only better questions. And in science, that is often how progress begins.